And I'm Anton.
And we're both PhD researchers here at the University of Birmingham.
And we represent the Battery Bunch.
So today we're going to cover all things lithium-ion batteries, how they work, so how they're made, and how we recycle them.
Lithium-ion batteries are everywhere. You can find them on your smartphone, laptops, and more recently, electric vehicles. Before going into how we produce our lithium-ion batteries, it is important to know how they operate. And I always believe this is quite important to know, especially when we make decisions as consumers, and more so in future as we switch to the electric vehicles instead of combustion engines. So in short, with any sort of battery, you'll have two electrodes and an electrolyte separating them both. So for a lithium-ion battery, what makes it special is it's rechargeable. So also you might hear it as a secondary battery. So in one of our electrodes, it will consist of a lithium transverse metal oxide, for example, but in short, we're going to call this an oxide electrode. And one of the examples is lithium cobalt oxide. And in this here, we have its crystal structure, where the purple layers represent the cobalt oxide and the blue spheres represent the lithium. And as we'll see later, this will be deposited on an aluminium current collector. And our second electrode is graphite. Some of you may actually know where graphite is in the classroom, and hopefully you're thinking in your pencil. And for the graphite electrode, instead of depositing on aluminium, we deposit on a copper current collector. And hopefully you can spot two similarities between these different structures. And I'm hoping you're going to say they're layered. And this is how we can relate this to Jenga. On charging, the lithium blocks are removed from the oxide electrode and inserted into the graphite electrode. We are now charging our battery. This is an uphill energy process. On discharge, the lithium blocks are removed from the graphite electrode back to the oxide electrode. We can also think about the rate of charge. So for example, I always like to think, well, you wouldn't plug your smartphone charger into an electric vehicle. You need to be, in terms of when we think about applications, we need to think of a sensible rate of charge. Not only because we don't want to damage our electrode, as you can see with our right-hand tower, but also we don't want to wait forever for our device. So we need to be quite careful that we don't damage our electrodes, but also that electrodes are suitable for use. And finally, we can also mention about degradation. So over time, our batteries will gradually fade in performance. And this is just due to, as you can see here, visual representation of charging and discharging, and only focused on the oxide electrode, just how our structure becomes disjointed and out of place.
While Anton is going to show you the Meta Map facilities, I'm now in the Stall of Chemistry and I'm all kitted up. I've got my lab coat, I've got my lab specs, and I'm ready to go in the lab. And I'm going to show you how the batteries start their life from the powder, and we'll work all the way up to a working battery. And as well, we're no longer outside in the cold and the rain, but you might hear, instead of the natural patter of rain, you'll hear the hum from some of our instruments that are currently working. So without further ado, let's go in.
So where do our batteries actually begin their life? So the starting point is actually in synthesis. And being a solid state chemist, our favourite route is called the ceramic but also solid state method. And actually what we do is we take our starting materials and we simply grind them up using a pestle and mortar. We then heat them up to high temperatures, so the powders, heat up several times to high temperatures. We then check on the X-ray diffraction, whether it's phase pure. We're now in the advanced materials characterisation facility. And the reason we're here is before we go anywhere near to making our batteries, we need to make sure the powders or samples that we have made are phase pure. And one of the ways that we do this is in our inorganic toolbox is X-ray diffraction. And here's one of our diffractometers.
You just saw me in the advanced materials characterisation facility. And I mentioned that our materials we have to make sure that they're phase pure. But what do I mean by that? So in short, we need to make sure that all our starting materials have reacted and that we have formed the structure type that we would like, because in this, it could affect how our batteries form. And I just want to point out, don't stress if you've never heard about this technique before, or you're not too sure what I mean with Bragg's law and that, We actually teach this at undergraduate year 2 level. Do you get any of this? Then brilliant. I just want to show you this as an example of some of the steps we take before getting to our batteries testing. And here is just an example of XRD pattern. And some of you might actually have in your classroom the sodium chloride structure. You might be more familiar with the bottom structure here, where you can see the ball and stick model, where the green would be your chloride and the yellow would be your sodium. So you've got sodium chloride. You sometimes might actually see it represented in another form with polyhedra. And this is just an example as well, right at the bottom, some of the data we collect and how this information can tell us our structure. Once we know our material is phase pure, we then have to ball mill it with an additive. After that, we are then ready to start the coating process.
Now needs to be made into an ink so they can be coated onto our current collectors. To do this, we add a solvent and mix until we have a good coating consistency. Too thin and it'll go everywhere. Too thick and it won't spread well. You can think of this step like making the icing for a cake. We have to gradually mix water into the icing sugar and make sure it is all well mixed. Once we have mixed the ink multiple times to achieve a good consistency, we are ready to coat it onto our current collector. We draw it down the current collector gently to form a thin layer of coating. We then allow the coating to dry before moving it into a vacuum oven. One of our researchers is now going to show us how to assemble a full coin cell. She has placed one of the electrodes into the coin cell bottom casing. Putting the electrolyte and the separator on top. Before adding more electrolyte and finally adding the second electrode. We looked at these electrodes earlier in the form of the Jenga, where we had the oxide electrode and graphite electrode. However, we did not mention the electrolyte. The electrolyte helps our lithium ions shuffle between the electrodes, whilst the separator, which looks a little like filter paper you may have seen in your school labs, provides a physical barrier between the electrodes. This prevents the two electrodes from touching directly and causing a short circuit in our batteries, which would render them useless. The final components of the batteries are spacers, a small metal disc, and a spring before adding the top casing. We then crimp this together to seal it shut. And voila, we have an assembled coin cell battery.
Once we have made our coin cell, we can then start to test it and see how well it performs. We're not just limited to the little coin cells, we can actually make far larger batteries. You can see here we're coating on a much larger scale. And also Anton has shown the different batteries beyond that coin cell.
Thank you, Professor Peter Slater, for joining me. I was hoping that you could answer a few of my recycling questions about batteries. And the first thing I'd probably ask is, so why do we need to recycle these battery packs? Why can't we just send them to landfill?
Well, there's a number of reasons why we need to recycle the battery packs. One is it's environmentally unfriendly and unsafe to send them to landfill. But another key thing is there's valuable raw materials in the battery pack that we can recover and then reuse to remake new battery packs. And so we've got a nice circular economy where our battery pack is used in the vehicle, it's recycled, remanufactured into new materials, and then reused in another new material.
With recycling, are there many methods? Is it quite difficult to do?
Well, in recycling a battery pack, there's a number of different parts involved. First, you have to dismantle to give you the individual battery modules and the battery cells. And then they can be either manually dismantled or shredded to get your materials, which you can then apply chemical methods to start recovering all the valuable metals that are inside.
This is our battery safety chamber, which is designed to be able to contain a battery fire. These incredibly thick doors and steel body means that it is the safest place for us to shred batteries. Inside here you can see our wonderful shredder, which is what we use to shred our batteries into small pieces that we can then separate out by physical processes. On this side here we've got a wonderful array of power plugs. We've got these orange gas detectors here, 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 and down there, which is designed to measure the oxygen content and HF content in here. We've also got a building management system here, where we can control the extraction in the safety chamber and other aspects of this building. We've got wonderful climate control in here for the comfort of our battery scientists.
Just like our electric vehicles reach 100% charge, we've also come to the end of our talk. Thank you very much for watching, and we hope you enjoyed our whistle-stop tour of battery technology and showed just how complex and how much chemistry is involved in these little devices, or should I say big in terms of EV. We wish you a very relaxing break and all the best for 2021. Thank you very much from the Battery Bunch.